Here is the 8th behavioral design pattern from the famous Gang of Four design patterns book. This one is called state pattern, and it is a pattern you use when you need an object to alter its behavior when its internal state changes. I'll start with a quick summary of what we are trying to accomplish with this pattern. The state pattern is a good choice when you are trying to accomplish the following. You have an object that cycles through two or more discrete internal states. The behavior of the object radically changes with each state transition. Let's go through the points one by one. In this scenario, we have an object in our application architecture that cycles through a number of internal states. These states can be very abstract. For example, something like idle, connecting, connected, disconnecting, and error. Each state is only accessible from a limited number of preceding states. For example, you can only transition to the disconnecting state from the connected state. So far, so good. The second requirement is that the object radically changes its behavior based on the internal state. So the same methods behave very differently for different state values. You can code this by hand by putting switch statements in each object method. But the disadvantage is that the code that corresponds to a single state is now spread out over all methods in your object. If you have lots of states with complex state transitions, then things can get complicated really fast. The state pattern solves this problem. The pattern concentrates all code corresponding to a single state into a single state class. It also makes each state responsible for selecting the next state in the cycle. For large state diagrams with lots of complex transitions, this simplifies things enormously. So, we've talked about the benefits of the state pattern. The pattern concentrates all code corresponding to a single state into one state object. This eliminates all complex switch statements that you would need if you do not use this pattern. The pattern also makes each state responsible for selecting the next state in the sequence. Again, if you do not use the pattern, you would have to place this code inside switch statements in each object method. The pattern allows you to place the code in the most logical place, the state class. The state pattern scales really well, and it can handle very large state diagrams with lots of complex transitions. But the pattern also has disadvantages. First of all, this pattern is a trade-off. The pattern concentrates all code corresponding to a single state into one state class. But sometimes this isn't what you want, because the pattern also spreads out the code of a single operation over many state classes, which can make the code hard to maintain. Another disadvantage is that you need to be very careful that each state has a reachable successor state. It is very common for state machines to hang in a specific state with no way out. You need to carefully design your state transition diagram to prevent this from happening. Okay, here is the UML diagram of the state pattern. I will start with the state class. This is an abstract base class that declares the methods that need to change their behavior due to changes in the internal state. In the diagram, only a single method has been drawn, called handle. The method takes a single argument, which is the reference to the current context. There are two classes derived from state, called concrete state A and concrete state B. Both classes implement the handle method. Each concrete state does whatever it needs to do to handle that state, and then changes the current state of the context to the next state. For example, concrete state A could change the context state to concrete state B. Then, when the context class calls the handle method on concrete state B, it could change the state back to concrete state A. This would create a state machine that is constantly cycling between these two states. The context class is in the top left corner of the diagram. This class has a public interface that is exposed to clients. The class also has a private state field that tracks the current state of the context. In the diagram, the public interface consists of a single method called request. When clients call the request method, the context class calls the handle method of the current state. The state does whatever it needs to do to handle the current state, and then it modifies the context to change the current state to a new value. This pattern constantly changes the behavior of the request method, as the current state of the context cycles through all possible values. I am going to use the state pattern to implement the software for a chocolate vending machine. My machine will be coin operated. After inserting €1 coin and pressing a button, the machine dispenses a single chocolate bar. I will create a class to represent the vending machine with 4 methods for inserting a coin, ejecting a coin, pushing the button, and dispensing a chocolate bar. The state classes will change the behavior of these methods based on a constantly changing internal state. My states will transition according to the following pattern: from no coin to coin inserted to sold, and then to either no coin again or to sold out. I will implement the pattern with the following classes. Okay, let's take a look at the code. So here is the abstract state base class. You can see the 4 methods here, implemented as abstract methods that must be implemented in the derived state classes. Let's start with the no coin state. Inserting a coin advances the vending machine to the coin inserted state. All other methods won't work, because no money has been inserted yet. Here is the coin inserted state. From this state, you can press the button to buy a chocolate bar, and this will advance the vending machine to the sold state. But you can also choose to eject the coin and get your money back. This will advance the vending machine back to the no coin state. And here is the sold state. In this state, only the dispense method will work. It dispenses the chocolate bar and advances the vending machine state back to the no coin state. That is, unless the machine runs out of chocolate bars. If that happens, the next state will be sold out. And this is the sold out state. In this state, none of the methods will work. A technician needs to restock the machine and manually reset it to the no coin state to make it work again. Okay, now let me show you the vending machine class. The class declares the 4 methods here and simply defers to the current state to implement the methods. In each call, the vending machine passes along the this pointer, so that the state classes are able to modify the current state of the vending machine. And finally, here is the main program method. It is a simple command line user interface that waits for the user to enter a number between 1 and 3. 1 corresponds to entering a coin, 2 means eject a coin, and 3 is pressing the button. Let me run the program to prove that everything is working. I'm compiling the code now. And I'm running the code now. Okay, let me insert a coin. Yep, that works. Now I'll eject the coin. And now I'll press the button. Nope, that doesn't work, because there is no money in the machine. So I will insert a coin again. I'll try to insert another coin. Doesn't work. Okay, so I guess I press the button now. And there's my chocolate bar. Now let me try to press the button again. Nope, doesn't work. And now I'll try to eject the coin. And that doesn't work either. So there you go. The vending machine works fine. Okay, here is a quick checklist you can use to implement the state pattern. First, identify a class that needs to change its behavior based on a number of discrete states. Refactor the class into a context class and define the context interface. Create a state base class that replicates all methods in the context interface. Each method takes one additional parameter, which is a reference to the context class. Create derived state classes for each discrete state. Each derived class only overrides the methods it needs to override. All context method calls are passed on to the current state object with the this value in an extra argument. And finally, each state changes the current state in the context object as appropriate. And here are some final comments. State objects are often singletons. And this makes sense when you consider that the pattern continuously transitions from one state to the next, which clutters the heap with lots of dereferenced state objects. When your application architecture has thousands of states and millions of possible state transitions, then you can actually run out of memory. By using singletons, you prevent this memory pressure. Another solution for very large application architectures is to use the flyweight pattern to share state objects. This combination of patterns will ensure that only the states with unique intrinsic state are stored on the heap, and nothing else. You can also combine the state pattern with the interpreter pattern. Interpreters often have a parsing context that determines how they will respond to sequences of expressions. You can use the state pattern to modify the behavior of the interpret method based on the parsing context. Okay, let me recap what we have learned in this lecture. The state pattern lets you alter the behavior of an object when its internal state changes. The pattern eliminates complex switch statements in the object methods. The pattern can sometimes hang if a current state has no successor state. States can be made singletons or flyweights to save memory. The state pattern can be combined with the interpreter pattern.